Hey guys, welcome back to another episode, and today we are going to be looking at differentiation. So this is really a video that's aimed at doing a refresher in differentiation versus an introductory video on differentiation. So at this stage on the left of my screen, you guys can see that I have a table of standard differentials. So what we're going to do is just revise a couple of these via some questions. So let's get into it. So looking at the first one, you guys should be able to recall if you have any function x raised to some power n, the derivative of that is simply found by writing your power in front as a coefficient, and then you rewrite your x variable present, and then you simply reduce your power by 1. Now, in order to differentiate something using the standard derivative, your questions should quickly match and look like the derivatives you are trying to replicate. So in this first question here, you can clearly see that it looks like the exact form of x to the power of n. Because it represents or it replicates that form, we are sufficiently able to simply apply this derivative to our final answer. So let's just simply differentiate this one and see how our answer is going to look like. So first of all, please remember to write dy dx. A lot of students forget and they write the equal sign right after, which is incorrect. A differential is not equal to your original function. Alright, so dy dx would be a perfect way to start your answer. And then we're going to follow along with how to differentiate something like this. So we're going to put that power 4 in front as a coefficient, and then you're going to follow up with x and reduce our power by 1. It's that simple. Alright, looking at our question 2, you would notice that it's no longer in the form of x to the power of n. Instead, we have a case scenario where we have several algebraic expressions inside there, several algebraic terms, will contain within brackets, and it looks like the form of the second one on the left hand side there, where we are seeing a chunk being all raised to the power of some n. In this case, our value of n is simply 7. So how would we attempt to do a question like this? Well, first of all, your notation should be correct. So we will begin by writing our answer as dy dx is equal to. Now, according to our second rule, you can see that what they do is they simply write the existing power once again as a coefficient. So we are also going to do the same. So we're going to bring down that 7 in front, have our 5x squared minus 3x plus 1, and also they reduce their power by 1. So our power is now going to be 6 after differentiating. Now there's also something special in your standard differential when it comes to a chunk. You notice that they have another coefficient, a, being present. And in order to get that value, essentially what you have to do whenever you have questions in this form, where it's a chunk to some power, is that you're expected to differentiate what is within your brackets. So differentiating individually what is within our brackets, we will get the following. So you multiply by, if you differentiate 5x to the power of 2, you're going to get 10x. And if you differentiate minus 3x, you're going to get minus 3. If you continue along and you were to differentiate that constant, positive 1, you would get 0. So you close your brackets, and what you have done in red is that you have simply differentiated your chunk contained within brackets. So that is how you would go ahead differentiating formats that are in this example, like these ones in this example. Now let's look at the third one. In the third question here, you can see we have an exponential function, and those are types like these. Now, this type of example looks more like the fourth one, because you can notice that the power is more a substantial format where we have an expression being written there. Now, when you're differentiating exponential functions, once again, you start off with your answer in the form dy dx being equal to something. Now, the beautiful thing about exponential functions is that after differentiating, your final answer always has a component of your original question. So we are actually going to rewrite that e to the power of 4x squared plus 2 as part of our answer. And generally, this is what you always do when you're differentiating exponential functions. You locate your exponential function and you rewrite that to whatever power the question has given you. The part of the exponential function that we actually have to observe when it comes to differentiation is the power involved in the question. So in this case, the power involved in our question is 4x squared plus 2. Now, if you were to differentiate that, you would get 8x. You would get 8x alone because the differential of plus 2, which is a constant, is simply 0. And you close your bracket. It's always wise to write your answer in brackets just in case you end up getting multiple terms that would affect the expansion of your final answer. In this case, because we have only gotten one term, it's safe to remove your brackets and write your answer as follows. And that's your final answer. So when you're differentiating exponential functions, once again, the key tip to remember is that you are essentially differentiating the existing power and you rewrite your question. Alright, let's move on to the last and final example I have in relation to this table. And that example is with a logarithmic function, or lns. So once again, we will begin by writing our answer in the form dy dx is equal to. Now you can see the standardized format when you differentiate ln of x is simply 1 on x. But by extension, if you were to have ln of some function, or if you want to call it a chunk, or what is contained within bracket, in order to differentiate that, so if I were to add an additional rule here, if you had ln of some function, then by extension, the derivative of that function is simply given by, you rewrite your function on the denominator, and then you write the differential of that function on your numerator. So considering that, we will simply observe our existing function contained within brackets, which is 2x plus 5, and we are simply going to rewrite that on our denominator. Now, we are going to observe that and in fact differentiate 2x plus 5. The differential of 2x plus 5 is simply 2. And we write that on our numerator. So you can see that it matches up with what is written here. So by extension, when you're differentiating logarithmic functions, it doesn't matter how many terms belong to within your bracket. You will always rewrite that under your divisor line or in your denominator. And your numerator always contains the actual derivative of what is contained within brackets. Unlike exponential functions, you'll notice that when you differentiate a ln function, your ln disappears. Those are some key tips to remember when it comes to differentiating algebraic functions that have multiple terms, exponential functions, and ln functions. So I hope that refresher was sufficient for you guys to get back on track when it comes to moving ahead into more difficult types of differentiation. On screen, you would see that I also have some standard differentials for some trigonometric functions, and they are sine, cos, tan, sec, cosec, and cot of x. All of these you would do well to memorize these standardized derivatives of these exponential functions. When it comes to doing upper school pure math, these types of derivatives will come into play in the future. And if you continue watching more of these videos, you will see some examples of these. For the remainder of this session, I would also like to review the product rule and the quotient rule. So stay tuned, that's coming up next. So thank you so much for staying on. So a frequent error that I always see a lot of students making when it comes to differentiating is that they tend to differentiate products of functions instead of using the product rule to differentiate. So for example, y is equal to 2x plus 3 is a function in and of its own. This is a type of an algebraic function. Now ln of x in and of its own is also a different type of function. It's a function in terms of ln x. Over here you can clearly see that we have two completely different types of functions. Now students may look at questions as follows: y is equal to 2x plus 3 and 5x squared plus 1. And sometimes they say both are algebraic functions, so therefore the product rule cannot be applied. This would be incorrect to say. A question like this can be differentiated one of two ways. The first way, you can simply expand your brackets using the FOIL method, and by doing so, you would end up getting 4 terms that can be differentiated individually. However, another way that you can actually do this question is by applying the product rule, where what's written in your first bracket would be called u, or your first function, and what is written in your second bracket would be represented by v, your second function. So just point to note in the future, when you are differentiating, your function does not necessarily have to consist of two different types of functions. So let's continue working the example above. Okay, so in this question, in order to apply the product rule, you must understand how to separate your functions. So in this question, 2x plus 3 is a function by itself. So we are going to let that first function u be equal to 2x plus 3. Secondly, we are going to let our second function v be equal to ln x. That way, this y is actually the product of two separate functions u and v. Next, what we're going to do is we're going to differentiate u with respect to x. That gives us 2. Differentiating v with respect to x from your table of values as shown before will simply give us 1 on x. Now it's time to put our product rule together. So our product rule goes as follows: dy dx is equal to u dv dx plus v du dx. And that comes from this rule up top. All you have to do once you generate these 4 terms is simply substitute into your rule. U, according to the question, is simply 2x plus 3. So we will write that in here. 2x plus 3. And we will contain it in brackets because it does have more than one term. dv dx is 1 on x, so let's replace it there. You can write it as over x, or you can simply choose to write down your 1 on x in brackets next to it. Next up, we're going to identify v, and v is ln of x, so we're going to write that here. And lastly, we're going to look for du dx, which happens to be 2. And when it comes to constants, you would put your numbers in front of your functions. Now, So we can clear this up by writing 2x plus 3 over x plus 2 ln of x. And that's our final answer. That's how you would apply the product rule. Now, I would also like to say many times you would see students differentiate this question as follows. They differentiate the first bracket to get 2, and then they also differentiate the second bracket to get 1 on x, and then they multiply the products of those derivatives. This is completely incorrect. You cannot differentiate individual chunks, individual functions, and then multiply the product of those derivatives. You will get an incorrect solution. So in the future, a very important thing you must be able to recognize is when you actually have the product of different functions. Okay, so let's look at an example for when we would actually apply the quotient rule. Up next. And we're back. So on screen, we have the quotient of two functions. You can clearly identify this. I think the quotient rule is easier for a lot of students to recognize than it is to recognize the product of two functions. So we have one function on the numerator. We're going to let that be equal to u. So we're going to say u is equal to cos of 2x, and we're going to let that function on the denominator be equal to v. So first up, before you can get into the quotient rule, there are some items you require. We need to find out the value for du dx. So we're going to differentiate u with respect to x. Now in this case, you can see that we have cos of 2x. So we're differentiating cos of a function. Whenever you're differentiating cos of a function, you must always remember to multiply your final answer by the derivative of that function. If you differentiate 2x, you'll simply get 2. Then you can move ahead and you can differentiate as you normally would cos of a function. The differential of cos is simply negative sine of x. But in this case, we are differentiating cos of 2x. So the differential of cos of 2x would be negative sine of 2x. And that is our final answer as to how you differentiate cos of a function. A side note for those of you who are still concerned about questions like these, if you had to differentiate y is equal to cos of 2x plus 2x squared plus 3, then the derivative of that function would simply first be equal to, you differentiate what's contained within brackets, and that gives you 4x alone. Then you identify what is the derivative of cos. It's negative sine. So you simply write in that negative sine, and you rewrite your entire function contained within bracket. That is your final answer. All right, so let's get back into our answer here. So continuing along, we need to get values for dv dx. So if you were to differentiate x plus 2, you just get 1. And then finally, we can take those values and we can successfully substitute them into our quotient rule that goes as follows. So on the denominator, you can see that we have v squared. So what is v? V is x plus 2. Therefore, v squared is going to be x plus 2 all squared. Please remember to write your brackets. Then we have a subtraction sign present in that quotient rule, and we begin with the letter v. Once again, v is x plus 2, and we're going to multiply by du dx, which is this chunk over here. I think we might need some more space. We're going to write that minus 2 in front, and then we're going to continue with our sign 2x. If you wanted to write the entire thing after the x plus 2, that's also fine. Next up, we're going to write u. Now u is cos of 2x. So So we'd write down cos of 2x. And then finally, we're looking for dv dx. dv dx is just simply 1. You can write 1 in brackets, or you can come to the understanding that at this stage, 1 is understood to be there. So that's our final answer. Some people may want to expand these brackets to get minus 2x minus 4, and you can do that as well. Or you can leave it as before. Alright guys, so that's the final answer. There are many things you can do with these questions. You can use the double angle formula to get identities for sine 2x and cos 2x, and you can simplify that numerator even further. But for this video, we are really focused on the application of the product rule and the quotient rule in questions, as well as being able to identify when to use these rules. So I will do one more example on the quotient rule, and then if you guys have additional questions, you could leave comments down below, and perhaps I might even do a full tutorial session on the product and the quotient rule. Alright, so on screen you can clearly identify that we have a quotient. And we are going to let that numerator be equal to u. And we are also going to let our denominator be called v. Now it's very important the letters you use, because the formula goes in a particular order. It's separated by a subtraction sign. So you must always remember that you have to call your numerator u and your denominator v if you were to follow along with the formula. So we are going to differentiate du. We are going to differentiate u with respect to x, and that just gives us e to the power of x. Next up, we are going to differentiate v with respect to x. Now, our function v consists of a constant and sine x. So when you differentiate that constant, you get 0. When you differentiate sine x, we simply get cos x. Next up, we are going to recall that dy dx using the quotient rule is a very long formula. And it looks as follows. You always start with v, and then you follow up with u. And it's always helpful to remember that the derivative associated with each letter actually opposes. So it's v with u and u with v. Now all that's left to do is substitution. Let's locate these letters. So on the denominator we have v being equal to 2 plus sine x. So we'll rewrite v wherever we see it. It also belongs here as well. Next up, we're going to identify our other letters. So we're looking for du dx, we're looking for u, and finally we're looking for dv dx. You see, when you lay out your question like this, it's very easy to not make simple mistakes. And I've always found that even as a teacher, writing it out like this helps greatly in reducing mistakes in the future. Looking at that numerator, if you wanted to, you could factor out that e to the x such that we will end up getting the following. Dy dx, retaining that denominator that's present, we'll factor out that e to the x component from each of these, and you would end up getting 2 plus sine x minus cos of x. And that's about your final answer. If you wanted to, you could have expanded the denominator and see if anything could have cancelled with a numerator. In this case, and in this example, we're going to leave our final answer as follows. Okay guys, so that was a gentle recap on how to utilize standard differentials for sine, cos, e to the x, ln of a function, as well as using the product and the quotient rules. I hope that was a nice refresher for those of you who forgot. And in the future videos, please look forward to us getting into implicit differentiation as well as partial differentiation and parametric differentiation. So stay tuned to this channel, guys. We have more to come, and I look forward to your messages and comments. And once again, if you have seen any mistakes in my videos, please leave a comment down below so I can make the relevant corrections in my description box. Thank you so much for supporting me, and I look forward to seeing you guys soon. Bye.